the vast silence of space, there is a star cocooned in wings of dust. A cosmic butterfly suspended in twilight. Its light does not simply shine, it struggles, scattering through veils of ice and shadow, carrying within it the first whispers of worlds. When the James Webb Space Telescope turned its gaze upon this hidden cradle, it unveiled a sight that stunned astronomers. A warped, tilted disk, glowing wings stretched for light, and the unmistakable signs of planets being born in the dark. What lies inside this chrysalis may rewrite how we understand the birth of entire solar systems and, perhaps, remind us of our own fragile beginnings. Welcome. You are watching Whisper Science. Make sure to subscribe and join us for more amazing science content. Now, let's move back to the video. A darkness deeper than midnight, punctured by wings of light. In the Taurus molecular cloud, some 525 light-years from what will be Earth's future horizon, lies a young star, a cocoon of gas and ice that whispers of worlds yet unborn. That is IRA SO4302-2247, known now to many as the butterfly star. It is a place where shadow and glow dance in delicate balance, where planets may begin their slow, secret symphony. Long before infrared telescopes could see through cosmic veils, astronomers had glimpsed the early signs of what later would be the butterfly star. Ground-based observatories recorded a nebulous glow in Taurus, hints of reflection, nebulae, above and below an unseen star, and a thick lane of obscuring dust between. The star's disk was observed edgy on its dark band, slicing through light. Early infrared and millimeter wave mapping showed substantial dust emission. Models tried to reproduce its silhouette. Those studies revealed dust grain growth up to tens of micrometers, settling toward the midplane and radial segregation. Larger particles closer in, smaller ones lofted higher in the envelope. The dark lane spans hundreds of astronomical units, and the envelope's faint, shimmering wings of scattered starlight betray a young star still feeding, still forming. Yet the instruments had limits. The resolution blurred details. Wavelengths could not penetrate the densest dust. Temperature gradients remained veiled. The vertical structured thickness, warp, symmetry were hazy sketches, not vivid strokes. The disk's inner region, possibly tilted or misaligned, was speculated but not confirmed. The jets and outflows hinted at unseen dynamics. But what forces shaped them, and how they interact with the growing disk, remained largely theoretical. Then came a new eye in space. The Webb telescope, with its near-infrared and mid-infrared vision, turned toward IRA SO4302 in a program designed to probe edge-on protoplanetary disks. What Webb saw was nothing like expectation. Twin lobes of glowing dust stretching above and below a thick, dark lane. Light scattering off dust grains at faint angles, a central disk opaque in places, translucent in others. The wings glowed in varying colors at infrared wavelengths. Wisps and radial variations hinted at asymmetry. Brightness shifted across each lobe. The dark lane was not uniform. Warp, tilt, misalignment were apparent, casting subtle shadows, altering the illumination in ways never clearly imaged before. Webb's instruments NIRCam and MIRI captured multiple bands, from near-infrared to around 21 micrometers, combined with optical data from earlier telescopes. A multi-wavelength portrait emerged. Size, shape, composition, and structure. The disk measures roughly 65 billion kilometers across, several times larger than our solar system. The wings' loose envelopes of scattering dust extend far, offering views of both the outer envelope and the inner structure. Clumps and streaks along the disk's edge suggest jets and outflows, material being ejected. Perhaps by magnetic forces, perhaps by accretion shocks. Light from the protostar, blocked by the thick midplane, escapes via the lobes, illuminating surrounding dust as reflection, nebulae. Shadows and brightness gradients show that portions of the disk closer in may be tilted relative to outer regions, perhaps hinting at a misaligned inner disk, or warp induced by unseen companions, or magnetic torque. Within that discovery is new data about dust grain sizes. Small grains persisting in the envelope, larger grains settling in the midplane. Evidence of dust settling is stronger than ever. The vertical thickness of the dust layer, how sharply it transitions, how it is warped, all of it visible. The interplay of light scattering and absorption gives clues to how dust is distributed. how dense zones block light, how transparent regions allow it through. And the temperature, warmer near the protostar, cooler outward, but complicated by illumination effects in the lobes. Earlier models had predicted these features, but Webb's data forces refinement. The inner disk tilt had been hypothesized in studies of Egeon disks. Now it shows up in the butterfly star, with real asymmetry in illumination and shadow. Jets and winds, long known but often faint, are more clearly outlined, their interaction with disk envelopes casting fine structure. The size and mass estimates of dust and gas must be revised. Human understanding of stellar nurseries has evolved. From mythic nebulae, as cosmic wombs, to telescopes revealing protostars within dense clouds, to radio and millimeter arrays mapping ringed disks, to now seeing Egeon disks with vertical structure, warp tilt, and complex dust behavior. The butterfly star stands as a bridge between what was known and what is only now being revealed. In its dark lane, in its glowing wings, lie the first patterns of how planets may coalesce, how chaos yields order, how dust becomes stone, how the universal tale of origin continues. A sudden gasp in the cosmic dark. The image that Webb delivered of the butterfly star shattered quiet assumptions. The disk, once thought to be a simple, flat ring of dust and gas, revealed complexity astonishing in its depth. Twin luminous lobes flank a massive, opaque strip of dust. But unexpectedly, that strip does not lie neatly aligned. It is warped, tilted, and carries shadow and brightness variations that had been undetected until now. For astronomers, this Egeon disk orientation is rare, but powerful. The warp in the inner region revealed through uneven illumination in the lobe suggests the inner disk is misaligned with the outer parts. This misalignment may be small a few degrees, but its consequences reach far. Shadows cast across the wings, brightness that diverges between the lobes, subtle asymmetries. These are not cosmetic. They are signs that forces, perhaps unseen, are shaping the disk in multiple dimensions. Disk tilt implies that material is not simply spiraling inward smoothly. Perturbations may be altering the flow, altering density, altering temperature. Even more shocking, the evidence for large dust grains settling toward the midplane is stronger than before. Yet, paradoxically, small grains persist in upper layers above the disk. This vertical stratification, with large grains heavy and sinking, combined with turbulence that lofts smaller ones, is part of models, but seeing it in so much clarity was not expected. The dark lane, thick and dense, blocks much of the starlight. Yet scattered glows and hazes, above and below, hint at active growth of dust. If dust grain growth from micrometer scale, toward millimeter and beyond, is already advanced, then planetesimals, kilometer-sized seeds, may be nearer than thought, even if not visible yet. The scale of the disk strikes awe, spanning tens of billions of kilometers. Several times the radius of Neptune's orbit, the protoplanetary material is massive. This is not a tiny cocoon, it is a vast reservoir, and its mass in both gas and dust appears sufficient to form giant planets. Yet the structure suggests that mass is not uniformly distributed. The inner warp, asymmetry, clumps, streaks of jet sol, hint at activity, at perturbation. Perhaps unseen companions tug at the disk. Perhaps magnetic fields twist it. Perhaps infall of interstellar gas, or misaligned accretion, impose angular momenta that differ across radius. The shock cuts deeper. Many edges on disks assumed symmetry. But here, scholars see that tilt and misalignment may be common. Researchers have surveyed Egeon disks and find that many display brightness, asymmetries, or inner region tilts. If the butterfly star is not an outlier but typical, many more planet-forming disks might carry internal warps. That could reshape theories of planet formation. Entire architecture of emerging systems might depend not only on radial zones, rings, gaps, but vertical structure, misalignment, shadowing, heating differences. Brightness variation across lobes implies temperature gradients, not simply radial, but polar, that is, above and below the midplane. The radiation escaping via lobes scatters off dust grains and envelopes, confirming that disk and envelope are still interacting, feeding, letting light leak along paths through less dense dust. The presence of jets and outflow streams of gas being expelled perpendicularly is stronger evidence now that angular momentum is shed or redistributed, that the young star is not only accreting, but also actively sculpting its surroundings. Perhaps most unsettling, planet formation may begin under more chaotic and uneven conditions than many models assume. Rather than a calm, flat disk feeding mass inward, the butterfly star suggests misalignment, warp, turbulence, heterogeneous dust distribution. All these might not be rare deviations, but fundamental features. The simplicity of many simulations may need recalibration. Planetesimals may form in shadowed zones, or warp-induced pressure traps. MASS may concentrate in crescents or clumps, not neat rings. Orbits might incline, planets may form with tilted axes, or even misaligned spin. This image forces a reconsideration of timescale. If large grains settling in warp exist already in a system this young, then deeper stages of planet assembly aerodynamics of pebble accretion, collisions, clumping must proceed faster, under more dynamic internal structure. The window during which gas giants can accrete before gas is lost may be tighter, influenced by how warped the disk becomes. The shock is that the butterfly star is no longer just a pretty mirror of textbook models. It is messy, dynamic, misaligned, and in that messiness lies the true complexity of creation. The calm assumptions of flatness, symmetry, uniformity give way to turbulence, warp, tilt, shadow. In the wings and shadows, in the illuminated misalignments, the mystery grows. How does order emerge from this chaos? How do planets take shape in such sculpted, twisted cradles? In the wake of Webb's revelation, the butterfly star has become a living laboratory. Its wings of dust and its dark lane no longer feel like a simple reflection nebula, but like a coded manuscript, waiting for the patient work of science to translate every line. Now begins the deeper investigation. The process of peeling back each layer of data, each photon, each subtle gradient of light. The first step is spectroscopy. When Webb's instruments dispersed the starlight that filtered through the wings, they revealed chemical signatures written across the spectrum: carbon-bearing molecules, silicates, water ice, and more exotic organics. Each with a specific fingerprint, leave delicate marks in the infrared. The presence of water ice is particularly telling. It clings to dust grains in the cooler regions of the disk, forming mantles that may one day be locked inside comets, planets, and perhaps even oceans on worlds yet to exist. In the butterfly star, these icy mantles are not mere chemistry. They are the seeds of future climates, the carriers of possibility. The distribution of dust grains also becomes clearer under scrutiny. Larger grains, heavy with mass, have begun to sink toward the midplane, while smaller particles remain suspended in higher layers. This stratification is not just a technical curiosity. It is the foundation of planetary birth. Settled dust concentrates, collides, and clumps. The midplane, hidden within the dark band that slices across the star's image, is the secret forge where pebbles will grow into mountain-sized bodies, where turbulence and magnetic fields decide which clumps endure and which dissolve. In the butterfly star, the evidence of this process has leaped from theory into observation. Magnetic fields, invisible yet pervasive, weave through the cloud. They guide jets, channeling matter outward in narrow streams, and at the same time press upon the disk, shaping it into its warped, tilted geometry. Astronomers long suspected that magnetic pressure could twist young disks, but rarely was there a canvas as striking as this one to demonstrate the effect. The butterfly's symmetry is deceptive. Closer inspection shows that even its apparent grace is bound in conflict forces, pulling, bending, resisting, yielding. The interplay between collapse and outflow deepens the mystery. Stars form when gravity pulls matter inward, compressing it until nuclear fusion ignites. Yet in the butterfly star, as with others of its kind, great volumes of matter are simultaneously expelled in jets and winds. This apparent contradiction is central to stellar birth. The disk feeds the star, but the star fights back, pushing some of that material away. Without this feedback, angular momentum would choke accretion. With it, the star finds balance. Webb's sharpness now shows how outflows carve cavities in the surrounding envelope, how they sculpt the wings of the butterfly itself, how they leave behind a history written in curves of gas and light. Computational models are tested against this reality. Supercomputers run simulations of collapsing molecular clouds, rotating disks, and magnetohydrodynamic winds. They predict warped disks under certain conditions, tilted inner regions under others, and grain stratification across scales. For years, these models were hypothetical, tested against blurred data. Now Webb's image offers ground truth. Where the models succeed, confidence grows. Where they fail, revisions begin. In this way, the butterfly star does not simply sit in the sky. It shapes the mathematics and physics of future generations of theory. It is here that the story circles back to history. In centuries past, humans looked at nebulous wings in the heavens and named them after butterflies, swans, or ghosts. Those shapes were metaphors for transformation, symbols of impermanence. Today, the metaphor acquires literal force. In the dust wings of IRAs 04302, metamorphosis is real. The transformation of microscopic grains into continents, into planets, into the raw canvas of worlds. The mythology of the ancients converges with the equations of astrophysicists. The deeper investigation reveals more than a picture. It uncovers a process, and a process is a narrative written in time. Each line of scattered light tells how dust settles. Each shadow across the lobes tells how disks warp. Each spectrum line whispers of water, organics, ice. Together, they paint a vision. A stellar chrysalis, not static, but alive. Not a photograph, but a symphony unfolding, measured in millions of years. The butterfly star is not just seen, it is interrogated, translated, understood in pieces. And in those pieces, the greater mystery only intensifies. The deeper the butterfly star is examined, the less it resembles a serene nursery, and the more it reveals itself as a battlefield of cosmic forces. What began as a strikingly symmetrical image soon collapses under closer inspection. The lobes that glow like mirrored wings show subtle differences: brightness in one side, faintness in the other, uneven shadows cutting across their forms. The once assumed harmony fractures into layered puzzles. The warped inner disk becomes the center of speculation. Why would its heart tilt at all? Gravity, in its purity, pulls inward symmetrically. If the disk were a simple collapse of a molecular cloud, it would spin like a balanced top. Yet here, something has shifted the symmetry. Perhaps a hidden planetary body, already forming, exerts its own gravitational tug, tilting the material around it. Perhaps a binary companion, too faint to yet emerge in the data, orbits nearby, pulling the disk into misalignment. Or perhaps the collapse itself was never uniform. Magnetic fields threading the Taurus cloud could have twisted the infall, locking in a tilt before the star was even fully born. Each possibility is dramatic. Each raises more questions than it answers. The light escaping through the lobes reveals additional complexity. Shadows flicker as if parts of the inner disk act like shutters, blocking light unevenly. This is not a quiet glow, but a projection of motion, geometry, and turbulence. What appears as tranquil wings could be the stage for chaos beneath, where clumps of dust rise and fall, and gas currents bend the very architecture of the cocoon. The persistence of small dust grains high above the disk only adds to the enigma. They should have long since settled or coagulated, yet they remain adrift, glowing faintly in Webb's vision. Their survival hints at turbulence that continually stirs the layers, like winds preventing sediment from ever settling at the bottom of an ocean. In such turbulence, the seeds of planetesimals may grow unevenly. Here accelerated, they're suppressed. If so, the planetary systems born from these disks may be more diverse, more chaotic than ever anticipated. Then comes the question of time. The butterfly star is young, still a protostar, still wrapped in an envelope of dust and gas. Yet the degree of organization and complexity seen already, the warp, the stratification, the ice mantles, is far ahead of schedule. Planetary formation may begin earlier than models have long assumed. The warp itself might be evidence that planets start shaping their environment when the star is barely alight. If so, then every star forming across the galaxy may be spawning worlds in its infancy, not its adolescence. The implications ripple outward. Planetary systems might not be rare masterpieces forged over long, calm epochs, but immediate companions born alongside their stars, struggling into being, while jets still roar from stellar poles. The comparison to our own solar system deepens the mystery. Was the Sun, billions of years ago, once shrouded in butterfly wings of dust? Did an early warp twist its disk, shaping the inclinations of planets, tilting the axis of Uranus, seeding the eccentricities of Pluto and other icy bodies? The butterfly star becomes a mirror, a possible glimpse of our own origin, frozen in another time and place. If our Sun emerged from such asymmetric chaos, then the very stability of Earth's orbit may be more fragile, more improbable than ever imagined. As scientists pore over the data, new models arise. In these simulations, tilted inner disks cast rotating shadows on outer regions, altering temperature, altering chemistry, altering where ESOs can form and survive. These moving shadows create shifting snowlines regions, where water, carbon monoxide, and other volatiles can freeze. If these lines migrate back and forth because of warp-induced shadows, the distribution of planetary building blocks would fluctuate wildly. Planets might form in bursts, then halt, then form again, sculpted not by simple radial gradients, but by the play of light and shadow themselves. What once seemed a single picture of beauty has become 1,000 open questions. The wings of the butterfly are no longer just reflections of light. They are signposts pointing toward forces hidden deep within. They suggest that planets may be forming in silence already, unseen yet exerting influence. They suggest that the act of birth is never clean, never smooth, but instead a restless negotiation between gravity, magnetism, turbulence, and chance. The mystery escalates with every analysis. Scientists are no longer content to admire the image. They are compelled to ask whether every disk across the galaxy hides similar warps, similar misalignments. If the butterfly is not unique, then planetary systems everywhere may be forged in this same twilight where chaos and symmetry blur, where shadows dance across newborn wings, and where the first outlines of worlds are etched into dust long before stars have finished kindling. The butterfly star stands at the intersection of observation and imagination, a canvas where physics and speculation intertwine. It is no longer enough to describe its wings, its warped lane, its scattering dust. To move forward, science must ask, what unseen mechanisms carve this symmetry and distortion? What hidden actors are shaping a star not yet fully born? And what lessons do these faint, twisted shadows whisper about the birth of planets everywhere? One theory rises first, the gravitational tug of a forming planet. Within the disk's opaque heart, clumps of dust and gas may already be gathering into a body massive enough to disturb the surrounding material. A nascent giant planet, hidden in shadow, could tilt the inner disk, creating the warp web has revealed. This possibility stirs profound consequences. If planets form this early while their stars are still young and unstable, then planet formation is not a delicate endgame of stellar adolescence, but an immediate companion to stellar birth. Every newborn star could bring worlds into being as swiftly as it begins to shine. Another speculation points to multiplicity. What if the butterfly is not a solitary star but a hidden binary? Two suns, entwined, could sculpt the disk with competing gravities. A faint companion, perhaps too dim to yet resolve, might tug the inner disk into misalignment, while the outer disk follows the system's broader momentum. Binary companions are not rare in the galaxy. In fact, they are common. If the butterfly is such a case, then its warped disk is not an anomaly, but a window into how dual stars shape the destinies of their planets. Magnetic fields emerge as another suspect. In simulations, magnetic stresses can twist collapsing clouds, channel gas into streams that arrive at the disk with differing angles of spin. Such misaligned infall produces disks with warped layers, outer zones rotating one way, inner zones another, shadows and tilts inevitable. The butterfly's symmetry of wings, crossed by a symmetry of shadow, could be the fingerprint of magnetism written into matter. If so, then magnetic fields, often invisible, may be silent architects of planetary systems, deciding how many worlds emerge and where they wander. Speculation does not stop with mechanism, it stretches into destiny. If warps are common, then the architecture of planets will reflect them. Worlds may form on tilted orbits, their planes inclined relative to their parent stars. This might explain the strange diversity of exoplanetary systems already discovered, hot Jupiters orbiting at skewed angles, planets with extreme eccentricities, systems where planets march in crooked patterns, unlike our solar system's order. Perhaps the butterfly star is not an exception, but the rule, a demonstration that planetary birth is born in disarray, and that our solar system's near-planar harmony is the outlier. The presence of water ice within the wings adds further weight to speculation. These ices, clinging to dust grains, are the building blocks of comets and oceans. If shadow and warp cause snowlines to shift, then the distribution of these ices would be dynamic. Worlds forming in the butterfly may receive volatile cargo, unevenly, one flooded with water, another starved, a third awash in exotic ices. The fates of climates, atmospheres, and habitability may be written here, in the simple play of shadows across a warped disk. More radical theories suggest that hidden turbulence, generated by the very act of collapse, keeps dust grains suspended, preventing them from settling smoothly. In this turbulence, eddies could trap dust, creating vortices that spawn planetesimals. Some models propose that entire planets may form in such vortices, clumps of gas and dust collapsing directly into planetary cores. If this is happening in the butterfly star, then its wings are more than reflections. They are signals of a maelstrom within, invisible yet decisive. Speculation turns outward, to philosophy. If every star is born amid such chaos, then planetary order is not guaranteed. The butterfly suggests that misalignment, tilt, and turbulence may be the cosmic default. Our own Earth, stable in orbit, drenched in oceans, may represent not inevitability, but fortune, an outcome of fragile balance rather than natural law. To see the butterfly is to glimpse not only the mechanics of a single star, but the precariousness of planetary birth across the galaxy. Some even imagine that the butterfly star hints at diversity beyond comprehension. If planets can form in warped, tilted, turbulent disks, then the resulting systems will be strange. Planets orbiting at skewed angles, atmospheres rich in exotic chemistry, worlds baked too close to unstable stars, icy giants drifting at tilted inclinations. The galaxy, through this one image, seems to declare that planetary systems are not copies of our solar system, but experiments in variation, each shaped by the accidents of its own chrysalis. In the end, the butterfly star becomes a metaphor, not by coincidence, but by physics itself. A caterpillar's cocoon is a place of dissolution, where cells break apart before recombining into wings. In I-arrays, 04302, dust dissolves into chaos before recombining into planets. What seems like symmetry conceals turmoil. What seems like beauty hides turbulence. And out of this, transformation emerges. Science will continue to test these theories. Some will fall, some will endure, others will evolve. But for now, speculation is necessary, for the butterfly star has given not clarity, but complexity. It has opened doors, showing that in the twilight of a young star, the universe experiments with countless paths of creation. The theories are scaffolds, fragile and shifting, built around shadows and light. Yet in those shadows lies the shape of worlds to come. Behind the ethereal image of the butterfly star lies an arsenal of instruments, algorithms, and collaborative effort. The shock of its warped wings and shadowed disk did not emerge by chance. It was the product of a long lineage of scientific tools, refined lenses through which humanity peers into the dark. To understand the butterfly is to follow the path of those tools, to see how machines orbiting far above Earth transform silence into revelation. The James Webb Space Telescope stands at the center, suspended at the L2 point, shielded from the sun by a 5-layer sail. It watches the universe in wavelengths the human eye cannot perceive. For the butterfly star, Webb's near-infrared camera NIRCam revealed scattered light from small grains, tracing the wisps above and below the disk. Its mid-infrared instrument MIRI probed deeper, sensing the glow of warmer dust and mapping ice signatures within the wings. These instruments did more than photograph. They dissected light into layers of meaning. Particle size, temperature gradients, density differences. Every pixel carried chemistry, every color contained structure. But Webb was not alone. ALMA, the Atacama Large Millimeter, Submillimeter Array in Chile, had already mapped dozens of disks in Taurus. Its arrays of antennas combined into a virtual telescope stretching kilometers across, sensitive to long wavelengths emitted by cool dust and gas. ALMA showed rings and gaps in face-on disks, revealing the fingerprints of forming planets. When its maps of dust distribution are compared to Webb's images, the result is a stereoscopic view of stellar nurseries. ALMA, tracing structure from the inside out, Webb illuminating structure from the outside in. Other instruments layer their perspectives. The Very Large Telescope in Chile, equipped with adaptive optics, captures visible and near-infrared glimpses of reflection nebulae. The Hubble Space Telescope, though now outpaced in infrared sensitivity, left a trail of earlier butterfly images blurry, yes, but now invaluable for comparison, showing how Webb's detail refines decades of groundwork. Together, these telescopes form a chain, each one extending the reach of its predecessor, each one handing the mystery forward. Yet the raw data from Webb and ALMA does not arrive as the dramatic image the world sees in press releases. It begins as streams of numbers detector counts, pixel arrays, spectra sliced into wavelengths. Supercomputers on Earth calibrate and filter, removing noise, correcting distortions, stitching exposures together. Data pipelines, tested for years before Webb's launch, convert raw starlight into usable science. For the butterfly star, these pipelines revealed the subtle brightness differences across its lobes, the faint curvature of shadows, the warping of its dust lane. Without this quiet computational labor, the warp might never have been noticed. Ongoing testing extends beyond a single star. Surveys now catalog dozens of edge-on disks, comparing the butterfly's warp to others. Are such tilts rare curiosities, or are they cosmic commonplaces? Instruments continue to scan the torus region, measuring polarization of scattered light, mapping molecules, tracing magnetic fields through their Zeeman signatures. Each dataset cross-checks the others, layering observations into coherence. Simulations run in parallel. Using magnetohydrodynamics and particle dynamics, supercomputers recreate collapse, disk formation, jet launching. Researchers adjust parameters, magnetic strength, turbulence. Companion presence do, see which reproduce Webb's warped shadows. These models are stress tests, not confirmations. They fail as often as they succeed. But failure is useful, pruning possibilities, tightening the range of explanations. Future missions stand poised to extend the work. The extremely large telescope in Chile, with its 39-meter mirror, will resolve protoplanetary disks at unprecedented clarity, perhaps even detecting embedded planets directly. NASA's Roman Space Telescope, planned for the coming decade, will widen the search, imaging thousands of disks across the galaxy. Each tool will test whether the butterfly star is unique or universal. The process is not just technological, it is communal. Teams across continents share data, debate interpretations, challenge each other's models. A warp scene in Webb's image is cross-examined with ALMAS maps. A chemical signature is debated across institutions. Peer review, often invisible, acts as the final instrument, sharpening claims, discarding unwarranted certainty, forcing humility before evidence. The butterfly star will not fade quickly from study. Its warped wings and tilted heart are benchmarks now, touchstones against which theories are tested. As new instruments come online, they will return to Taurus, checking whether time itself alters the star's wings. Over decades, snapshots may become a film, showing whether the warp shifts, whether shadows migrate, whether planets truly emerge from the lane of dust. The tools of astronomy are more than metal and mirrors. They are extensions of human curiosity, fragile machines hurled into the void to answer ancient questions. Through them, the butterfly star transforms from a silent glow in Taurus into a revelation, a case study, a riddle. Every tool, every test, every simulation is part of an unfolding dialogue between the universe and those who seek to understand it. The butterfly star is more than a scientific object. It is a mirror held up to the cosmos and to us. In the silence of the Taurus molecular cloud, it rests in its chrysalis, wings of light stretched against the dark, an image captured by machines orbiting far above Earth, yet its meaning flows beyond physics and dust. It is a meditation on beginnings, on fragility, and on the transformations that define existence. The butterfly, as symbol, has haunted human imagination for millennia, in myth and in art. It is the emblem of metamorphosis, an earthbound caterpillar dissolving into formlessness before emerging with wings. The image Webb delivered makes the metaphor literal. Here, a star dissolves its envelope, its dust swirling in chaos, even as it forges the seeds of planets. In its wings we see the shape of transformation itself, matter breaking, recombining, striving for new order. Every planet that will ever circle this star is contained in that image. Oceans, mountains, atmospheres, entire worlds remain hidden in those shadows. The water that one day may fill their rivers is now ice clinging to dust grains. The stone that may one day form countenance lies as silicate powder adrift in the lobes. In those wings lie futures, not yet written landscapes, awaiting their chance to exist. To witness them is to glimpse destiny still sealed in twilight. For Earth, too, the parallel is sobering. 4.5 billion years ago, our own sun likely passed through such a phase. It may once have worn butterfly wings of dust and gas, scattering starlight into the void. Our oceans, our air, our lives were written then, long before the crust cooled or the first cells stirred. When we look at the butterfly star, we are not merely studying another system, we are remembering our own. The warped lane, the tilted disk, the restless shadows, these remind us that birth is rarely perfect. Order arises through chaos, and stability is purchased by turbulence. The Earth's gentle orbit, the balance of its seasons, the presence of its seasons may not be universal gifts, but fragile outcomes of a turbulent process. To see the butterfly is to recognize that our own existence rests on improbability, on the delicate settlement of dust in a storm. Yet there is hope woven into the wings. For if chaos can give rise to planets, if turbulence can sculpt order, then life itself is testimony to the universe's strange capacity to create meaning from disorder. The butterfly whispers that beginnings need not be smooth. They need only endure. Out of asymmetry, stability can grow. Out of shadows, light can spread. In the philosophical hush of this image, time itself feels altered. A snapshot of a star, millions of years in the making, reaches us as if from the future and the past at once. It is young, yet ancient. It shows what has always happened, yet what has not yet happened here. In its twilight wings, we see the continuity of creation, the cycle of dissolution and rebirth that binds stars, planets, and life. The butterfly star closes this narrative not with answers, but with perspective. It teaches that the universe is not a clockwork unfolding with rigid clarity, but a vast field of possibility, shaped by accidents and alignments, by warps and shadows. It reminds us that beauty and mystery are not separate from science, but born from it. Each equation tested, each photon captured, carries not just data, but awe. And so, the story of the butterfly star ends not with finality, but with an open horizon. In cosmic twilight, wings of dust shimmer, holding the promise of worlds. Humanity, fragile and brief, has caught a glimpse. That glimpse becomes memory, and memory becomes wonder. For in the butterfly's wings, both the cosmos and our own existence whisper the same truth. Transformation is the essence of all things.